Oh, okay. So we should leave and come back at 1:50.
Hello, anyone here? Please, what's going on?
Hello, good afternoon. Um, is this the online class for Takrade Sunyani Boga? Hello, can you hear me?
Yes, yes, Doc. We are here.
Yes.
Let's
All
go.
right. So earlier this morning, it rained heavily here, and then we had challenges with internet and power. It's now being restored. So please kindly give me some few minutes. I will project my slide, and then we will start something. Okay.
Okay, Doc.
Yes,
So be online and wait for me. Thank you.
Hello. Hello.
Hello.
Good afternoon.
Yeah, afternoon.
Please, do you have any information?
What? Oh, we are waiting for Doc. He said 150. So
Yes. Do we have any information from him?
not
Yeah,
yet.
Doc said
Hello. He told
in the
us
morning we were having class with
it
him.
was raining
Not
heavily.
Yeah, he was
Hello,
saying, yeah, the network.
He said the network, so he
please.
will come to us. So
Yes,
he will come back
just stay
to
online.
come
I'm sharing my slide. Just be online.
with it. Okay.
Please, good afternoon once again.
Good afternoon.
Good
Good
afternoon,
afternoon, sir.
Yeah, the day has not been smooth at all. So pardon me
sir.
for the late start of the class. And let's see what we can do for the time ahead. So we were to start the reactions of aldehydes and ketones. That's where we got to last week. And so we're going to have a look at one or two.
Yeah,
Robert, lectures have begun. So aldehydes and ketones are reactive. They don't behave like the alkanes. They are reactive. And these aldehydes and ketones undergo what we call nucleophilic additions reactions. And so we'll be looking at some specific reactions that aldehydes and ketones undergo. But then in terms of comparison, we need to know aldehydes and ketones, which one is more reactive, and the reasons why that. And so aldehydes are more reactive in nucleophilic additions than ketones. So whenever we are looking at nucleophilic addition reactions, aldehydes are more reactive than ketones. The reason that favor aldehydes in this regard are both steric and then electronic factors. Now with the steric effect or the steric factor, if you look at the aldehydes, and for that matter, their functional group, you realize that the carbonyl carbon and then the carbonyl oxygen, that is to say the carbonyl functional group, is surrounded by one alkyl group and a hydrogen. So if you can see my cursor, this is an aldehyde functional group, and then around the carbonyl, there's this R group here, and there's this hydrogen group here. You know, alkyl groups or area groups, which are normally represented by the R, are bulky groups, and for that matter, they occupy space. But then in the case of the aldehyde, we have only one of the alkyl group or the area group, and then a hydrogen. Whilst if you look at the ketone functional group, you have two alkyl groups around the carbonyl functional group. What this really means is that in the case of steric hindrance or steric effect, the carbonyl functional group is polarized. The oxygen is partially negative, and then the carbonyl carbon is partially positive. So a nucleophile can attack the carbonyl carbon for it to form your desired product. Now, if the nucleophile that is coming has very limited space to get to the carbonyl carbon, then that reaction will be a bit slow or slower. And so in the case of the aldehydes and ketones, because the ketones have two alkyl groups, what it means is that there is very limited space around the carbonyl carbon for the incoming nucleophile to reach out to it. And this is what we call steric effect or steric hindrance, meaning we have a lot of groups that is surrounding the carbonyl carbon, depicting an overcrowding situation, which is going to prevent any incoming nucleophile to easily reach out or access the carbon for the reaction to continue. But then in the case of the aldehyde, because there's only one alkyl group and then a hydrogen, hydrogen is very small in size. There is quite a considerable space around the carbon. So any incoming nucleophile can easily reach out to it and then attack it for the reaction to continue. So on the reason of steric hindrance or steric effect, the ketones are sterically hindered as a result of what? The two R groups around the carbon, while the aldehydes are less sterically hindered. And so it's a platform for nucleophiles to easily what? Attack the carbon for a reaction to take place. So that is the steric effect. Aldehydes are less crowded than ketones, and thus the tetrahedral product resulting from the aldehyde is more stable than that of ketone, as I've explained earlier on. The second effect, which also favors aldehydes than ketones, and for that matter makes aldehydes more reactive than ketones, is what we call the electronic effect. The electronic effect. Now, the carbon of aldehydes is more electrophilic than in ketone. And here, what we are saying is that if you are talking about nucleophilic reaction, a nucleophile is coming in, and nucleophiles are negatively charged. So they are looking for a positive center, an electrophile to attack. Now, both aldehydes and ketones have this positive center, and that is the carbon. But then, in the case of the ketones, the two alkyl groups here are said to be what? Electron donating groups. They are said to be what? Electron donating groups. Alkyl groups are electron donating groups. So as you can see from the red arrow, the two R groups are pushing electrons to the carbon, which is positive. What that implies is that they are making the carbon less positive. And so in a nucleophilic addition reaction, if the center of our reaction or attachment is less positive, then that reaction, that nucleophilic reaction, will be a bit slow. But if you look at the aldehyde, the hydrogen is not an electron donating group. It is not pushing an electron. It is only one alkyl group that is pushing electrons to neutralize the positive effect here. What it means is that comparatively, the carbon here will be more positive in the aldehyde since it's only one alkyl group which is neutralizing its positive effect, as compared to a ketone where there are two alkyl groups donating electrons to neutralize the positive effect. So on the level of electronic effect, we say the aldehydes are more, the carbon in aldehydes is more positive. And that allows for easy nucleophilic attack that will result in the product formation. But then the ketones are less electropositive in terms of the carbon in there. And so that makes it to react with a nucleophile in a much slower manner. So that is these two effects. So one way that we normally ask you question here is, an aldehyde and a ketone are both reactive. But then aldehydes are more reactive than ketones. And we'll ask you to explain your reason, the reason why aldehydes are more reactive than ketones. And the reason to use is the steric effect and the electronic effect. And so you explain based on these two effects. So these are just explaining all that I've just given you. Now let's look at nucleophilic addition reactions. Okay, the use of oxygen nucleophiles. Now, if you take a ketone like this one, if you take a ketone like this one, the alpha hydrogens of carbonyl compounds are acidic. Okay. And if you want to compare the acidity of the alpha hydrogen in ketones to that of aldehydes, again, the aldehyde alpha hydrogens are more acidic than the ketones. So here you could see that the pKa value for the aldehyde is 17, whilst the pKa value for the ketone is what? 20. Of course, the smaller the pKa value, the higher the acidity of the carbonyl. Now, the carbonyl group is strongly electron withdrawing, and when a carbonyl compound loses an alpha proton, the resulting enolate is stabilized by delocalization. And the enolate is the conjugate base of both the enolate and the keto forms. That's the enol and then the keto forms. And so that is what is being exhibited here. So aldehydes and ketones bearing CH bonds in an alpha position are weak acids. They are weak acids. And depending on the structure of the carbonyl compounds, the pK of a CH group are found in the range of what? 17 to 20. And so earlier on, I said that the aldehydes are 17, and then that of the ketone is what? 20. So if you have these alpha hydrogens which are acidic, then you expect that when there's a base, a strong base that is added, then that strong base can abstract a proton from this alpha position, and a carbanion is then formed. A carbanion is then formed. So that is what is being exhibited here. This is a ketone, and these two hydrogens are the alpha hydrogens. So when a strong base picks on one of them, its bond break onto this to form a double bond here, and then the carbonyl double oxygen will break and then form this one. And these two are said to be what? Resonating with each other. Okay, they are said to be resonating with each other, and that's what we mean by resonance stabilization. If you look at the acidity of 1,3-dicarbonyl compounds, there is a methylene group between the two carbonyl groups, and it is the most acidic in the molecule. So all that we are saying is that if an aldehyde has one carbonyl group, a ketone has one carbonyl group, and then you have a situation where a particular compound has two of the carbonyl groups, then you see the methylene group here, the one labeled in red. Those hydrogens are said to be what? Very, very acidic or extremely acidic. And that matter, they will aid in the reaction process. And I said, the smaller the pKa value, the stronger the acid. So if you look at a carboxylic acid, the normal carboxylic acid, acetic acid, its pKa value is what? 5. And if you compare to a 1,3-diketone, which has a pKa value of 9, and then of course a diester with a pKa value of what? 11, then that should tell you that the diketones with a methylene group in between them is very, very, very acidic. It's even more acidic than what? An alcohol with a pKa value of 16. All right. So one of the reactions of aldehydes and ketones is what we call the aldol condensation. And in this reaction, it involves two molecules of an aldehyde that combine to form an alpha beta unsaturated aldehyde, and then a water as a byproduct. So aldehydes and ketones can be converted completely to their enolates or enolates by using lithium diisopropyl amide, that is the reagent. So if you see this, that is the lithium, the anion of what? From the lithium diisopropyl amide. So when there is a ketone here, then the adjacent carbon, which contains hydrogens, the hydrogens are said to be what? Alpha hydrogens. And these alpha hydrogens are what? Acidic. They are acidic. So first of all, the base can pick on the acidic hydrogen, one of them, and then the bond of the carbon hydrogen will break and form a double bond here. If you are forming a double bond here, then this carbon cannot maintain the carbon double bond oxygen. So that one will break onto the oxygen, and then you form this product, which we call the alpha beta unsaturated aldehyde. Now, if you also treat the aldehydes and ketones with bases such as the hydroxide and then the alkoxide ions, they give an equilibrium mixture of the carbonyl, and this enolates and carbon-carbon bond formation can occur. So over here, you have two moles of what? Acetaldehyde. So what is happening is that for one of the mole of aldehyde, that's acetaldehyde, the base here will pick on one of the acidic hydrogens here, that's the two hydrogens here, and then the enolate ion will bond to the other molecule of what? Aldehyde, to form this aldol product, as you can see here. So the RCH2CHOH is the second aldehyde that comes in to react with what? The first one, which had formed an enolate product. So when the two aldehydes are joined together by a carbon-carbon bond, that reaction is what we call the aldol addition. Aldol addition or aldol condensation. I will share this lecture slides with you, so you can later, as you watch the recorded lecture again, you can look at it again, because for some of these reactions, it requires some time for you to sit down and then go over before you get used to them. So this is the mechanism for aldol condensation. As I've explained earlier on, the base will pick on the acidic hydrogen here, and then you form the enolate. Now the enolate, when it gets another 1 mole of an aldehyde, the carbanion, that's the carbon with a negative charge, will then combine with what? The carbonyl carbon of the next aldehyde, so that it creates another carbon-carbon bond between the two aldehydes. And when you do that, the carbonyl oxygen will break and form an anion, which we call the alkoxide ion. Now, the alkoxide ion, when you hydrolyze with water, forms an alcohol. Okay, so now you have the two aldehydes joined together with the carbonyl functional group and an alcohol functional group forming, and that is what we call the aldol product. The aldol product. And of course, when you form the aldol product, you can still continue. If you have more bases, you can still continue, because The new aldol product you have formed also has these two acidic hydrogens, which can also be removed by a base. And when that happens, the carbanion that you form here can also form a double bond with these two carbons, and then you have the hydrogen, that's the OH breaking off, and then you form this benzyl acetone, that's what we call the enone. Okay, so these are aldol condensation, and that is the detailed mechanisms. And please, my advice is that when you get a slide, you take your time and look at it. Definitely, as far as this course is concerned, you will not be asked to show the mechanism. Okay, what is important here is that the two aldehydes that is coming together to form the aldol product, you should be able to know those ones. So if I give you an aldol product and I ask you what two aldehydes, okay, resulted in the formation of that aldol product, you should be able to tell me the two aldehyde products. And of course, when I give you two different aldehydes too, you should be able to, under the right conditions, you should be able to tell me the aldol product that can form or result from them. So these are more examples to what we just talked about. What we are saying is that if you form the aldol product, there are other things that can also take place. If I'm able to take water from the aldol product, I can also introduce a double bond here, and that is what we call the aldol condensation product. Okay, so this is the aldol addition product, and then this is the aldol condensation product. So please know the difference. The aldol addition product, when you join the two aldehydes, you realize that you have the carbonyl functional group and then an alcohol functional group. That is the aldol addition product. And the aldol addition product, you can dehydrate it by removal of water. That is the OH, and then the adjacent hydrogen by introducing a double bond between the two carbons. And that gives you the aldol condensation product. So over here, you have acetaldehyde and then another acetaldehyde. These two are aldehydes. And these metal hydrogens are all acidic. So the base will pick on one of them, then you form the enolate. Then the enolate ion will attack the second acetaldehyde, and then this carbon double bond oxygen will break and then pick on a hydrogen, and then you form the aldol addition product. And any aldol addition product, you will see the aldehyde or the ketone, or more or less the carbonyl functional group, as well as what? An alcohol functional group. In between the two, there is always a methylene group. And the methylene group, the two hydrogens there are more acidic. And so in the dehydration reaction, you can remove the OH and then one of the acidic hydrogens here by forming a double bond, and that gives you the aldol condensation product with a double bond present. So the product of aldol addition undergo dehydration, as I've said, on heating to form the alpha beta unsaturated aldehyde. So this is just a summary of what I've said. And the conjugation of the double bond with the carbonyl group stabilizes the product. So you could see that in any aldol product, the aldehyde or the ketone functional group here, that's the carbonyl functional group, is in conjugation with the double bond that is formed. And this can undergo what we call resonance stabilization, and that makes the product very, very stable. So if you consider the same aldehyde, let's say 2 moles of it, okay, then you are forming an aldol condensation product of twice the number of carbons in the aldehyde that was used. But we can as well also have what you call the mixed aldol condensation. Mixed aldol condensation here means one of the reactants can form an enolate, or one of the reactants is more reactive towards nucleophilic addition to its carbonyl group than the other. So ketones do not readily undergo self-condensation, unlike aldehydes that can undergo self-condensation. And the reason is that, you know, aldehydes are more reactive than ketones, and I've already given you the reasons. The electronic factor as well as the steric factor. Now with the mixed aldol condensation using aromatic aldehydes normally involves spontaneous dehydration. It normally involves spontaneous dehydration. Mixed aldol condensations in which a ketone reacts with an aromatic aldehydes is what we call the Claisen-Schmidt condensations. Claisen-Schmidt condensations. Now let's look at the halofoam reaction, which is also found in carbonyls. And this is a reaction where a halofoam is produced by the exhaustive halogenation of a metal ketone in the presence of a base. So the condition is that if you want to form, or if you want a positive halofoam reaction, then the starting material, one, should be a metal ketone. The metal ketones usually undergo these halofoam reactions. And here, the halofoam is CHX3. Of course, the X here represents the halogen, okay? It represents a halogen. The X there represents a halogen. It could be chlorine, it could be bromine, and then the other halogens. So if you have R2CHCr double bond O, this is a metal ketone. So when you react it is what? A halogen in alkaline medium. Place the X2 here, could be Cl2, that's chlorine. It could be Br2, okay, that's bromine. So it does so in the alkaline medium. And what is happening is that the halogen replaces this acidic hydrogen here. It replaces this what? Acidic hydrogen. And then you form this particular product. Now, if you look at the equations beneath, the metal ketone reacts with the halogen in an alkaline medium, and first you form the carboxylate ion and then the iodoform product. And here the iodoform product, because we are representing X by the halogens, it's going to be a trihalomethane. It could be CHCl3, it could be CHBr3, it could be CHI3. And so when you use iodine as your halogen, then that's what we call the iodoform test or the iodoform reaction, in which case you are going to form triiodomethane as your iodoform product. And this images down here, it is just showing you the mechanism of the reaction of the metal ketone. So you have acetone, which is reacting with bromine in alkaline medium. The first step is that the halogen, that's the bromine, replaces one of the acidic hydrogens. And then if there are more acidic hydrogens, then in the presence of what excess bromine, you go to have a second bromine replacing a second acidic hydrogen. And then it keeps on until all the acidic hydrogens are replaced with what? Bromine. So you see the CH3 here, all the hydrogens have been replaced with the bromine. So we now have what? CBr3. Okay. So now the base can pick on the carbonyl carbon, and then by resonance stabilization, the CBr3 will break off as the iodoform. Okay, when it breaks off, it then picks on the hydrogen from the water molecule, and then you form your tribromomethane. So that is because we have used bromine. If it was chlorine, you form the trichloromethane. If it is iodine, you form the triiodomethane. And of course, the specific one in the use of iodine, that's where we normally call it the iodoform test. It is always a positive test for metal ketones. Then oxidation reactions of aldehydes and ketones. Of course, ketones are not oxidizable. The aldehydes are oxidizable to acids. So if you have a ketone like this and an aldehyde like this, both undergo oxidation with ammonium silver nitrate solution, and then the aldehyde is forming what we call the silver mirror PPT. Okay, and over there, the silver mirror precipitate will tell you that the carbonyl compound is an aldehyde. The ketone will not react, and so there will be no reaction. So ketones, in contrast, resist oxidation by most oxidizing reagents, including potassium bichromate and molecular oxygen. If this reaction is carried out properly, the silver metal precipitates as a smooth mirror-like deposit on the inner walls of the reaction vessel. Can somebody tell me why aldehydes are oxidizable, but ketones are not? Why aldehydes are oxidizable, but ketones are not? Yes. Anybody? Yes, go ahead. Are you there?
Yes, Doc.
Yes. My question is, why are aldehydes oxidizable but ketones are not?
Sir, I think it's because of the presence of hydrogen.
Presence of hydrogen where?
In the aldehyde.
So what does it do? Hello? Yes, you are right. The aldehyde, the carbonyl group of the aldehyde, you can see that there is a hydrogen here, which is absent in the ketones. So what it means is that the aldehydes have what we call the oxidizable hydrogen, and that's why they are easily oxidized. The ketones do not have any oxidizable hydrogen. So in terms of oxidation, you can use this oxidation to distinguish between an aldehyde and a ketone. Okay. And if we are to be specific with the oxidizing reagent, here we can have the Tollens test, the Fellens test, okay, the silver mirror test, and that's what you can see there, that the aldehyde is able to react with the ammonium silver nitrate to form the silver mirror PPT, which is a positive test for the presence of what? An aldehyde. But a ketone will not react with ammonium silver nitrate solution to forming any PPT. And that also confirms why it's a ketone. Then another oxidation.
Hello, Doc.
Yes.
Doc, please let us go back to where aldehydes are oxidizing agents. The earlier slides.
Yeah, this is the oxidation.
So, we said because of the hydrogen that is attached to the aldehyde structure, with explanation given, it means it's accepted. Now, they said oxidized to a carboxylic acid by a variety of oxidizing agents. So KMNO4 is an example of oxidizing agent. HNO3, the chromium, the chromate, the CHE2 and CHE204D are the examples to the aldehydes as an oxidizing agent.
Your line is a bit faint, but if I understand you well, you're asking whether all these ones are oxidizing reagents. KMNO4, nitric acid, chromic acid, potassium dichromate, right? Because I've indicated here that aldehydes are oxidized to carboxylic acids by a variety of oxidizing reagents. And these oxidizing reagents, we have listed them here. Okay. Hello?
Okay.
Yes. Just that if you pick the ammonium silver nitrate as an oxidizing reagent, that one, assuming you are doing this test or reaction in the lab, and then you put an aldehyde in a test tube or a beaker, and you add ammonium silver nitrate, the physical observation that you see that the aldehyde had reacted is a silver mirror precipitate that forms at the inner walls of the test tube or the beaker, which if it is a ketone, you will not see it, meaning that the ketone will not react because they are not oxidizable. So this is another oxidation, another type of oxidation. We said all those oxidizing reagents there, ketones do not react with them because it doesn't have oxidizing hydrogen. But we have what we call the Baeyer-Villiger oxidation of ketones. Another way that you can oxidize ketones is the use of the Baeyer-Villiger oxidation. And this reaction of ketones takes place with what we call the peroxy acids. Peroxy acids. And when they are used on ketones, you form esters. Form esters as a result of the insertion of oxygen from the peroxy acids between the carbonyl group and one of the attached carbons. So if you have a ketone like this, and then you react this ketone with a peroxy acid like this, what it means is that one of the oxygens from the peroxy will be inserted between the carbon of the ketone and then the R group. And that leads to the formation of what? An ester. And then carboxylic acid. The peroxy acid then is converted to what? A carboxylic acid. So this particular Baeyer-Villiger oxidation is for ketones. Okay, it's a special type of oxidation, even though ketones do not have oxidizable hydrogen. The Baeyer-Villiger oxidation works on ketones. And here, the product is an ester, and the ester that you get is the same as the ketone you are starting with. The only thing is that you are introducing or inserting an oxygen between the carbon and then one of the alkyl chains. So take note of the Baeyer-Villiger oxidation of ketones. And then the type of oxidizing reagent that's there. Yes.
So Doc, please, with the peroxy acid, as it reacts with the ketone, you see that the product you are giving is ester. Now, you said that one of the oxygen will go to come and
will be inserted between the carbon and then the alkyl group.
The alkyl group. So here, the carboxylic acid, one O is missing, O is correct, because the O there is forming a ketone on the second carbon atom.
Yes. Was it a question or a contribution? Because what I said is actually, what I said is actually what you are also saying.
I'm saying that with the first answer here, the peroxy acid is supposed to be
your line is not stable. Please, your line is breaking. Only work on it and get back again.
Thank you, Doc.
So in the oxidation of ketone using the peroxy acids, that's the Baeyer-Villiger oxidation, we are looking at the choice of groups available to migrate in a reaction. And we call those one the migratory aptitude of each group must be considered. In the Baeyer-Villiger reaction, primary alkyl groups are much less prone to migration than secondary alkyl or area groups. So generally, the more substituted groups, they migrate. Okay, they migrate. So if you have a ketone like this, you have a CH3 and a CH2CH3, then you are performing Baeyer-Villiger oxidation. Where should the oxygen from the peroxy acid go to insert? Is it between the carbon and then the methyl carbon, or the carbon and then the ethyl carbon? Definitely it's going to be the carbon and then the ethyl carbon, because we are looking at what? Which of the two alkyl groups is what? Highly substituted. Okay, and that is this one. So that will be the major product. It doesn't mean that when the oxygen here comes here in between the carbon and then CH3, it will not be formed. That will be formed, but then as a minor product. That will be formed as a minor product. Now, if you look at the cyclohexanol here, there are two carbons which are adjacent to the carbon, and so the oxygen can come in between any of them and then the carbon. But if you look at the carbon here, it is highly substituted than the one here. And so preferably when the oxygen comes here, you get a major product. But when you bring the oxygen here, you form a minor product. Then let's look at the reduction reaction. We are done with the oxidation. Reduction reactions. Remember that in alcohols, we got to know that when you oxidize a primary alcohol, you form an aldehyde. And then these aldehydes are further oxidized towards an acid. And that's, if you want your product in the aldehyde product, then as soon as you form the aldehyde, you should distill off quickly. If not, and it stays, it will be further oxidized to an acid. Or we were advised to use mild oxidizing reagent. And this mild oxidizing reagent, the common one was what? PCC, pyridinium chlorochromate. And when you use PCC, it then oxidizes the primary alcohol into the aldehyde product. So therefore, if you have an aldehyde and you reduce it, you should get back your primary alcohol, because oxidation and reduction are what? Reversible, or they are opposites, in action. So you oxidize a primary alcohol, you get an aldehyde. Then when you reduce an aldehyde, you should get what? A primary alcohol. Also, when you have a ketone and you reduce it, you should get a secondary alcohol, because during the alcohol reactions, we got to know that secondary alcohol are oxidized towards ketones. So please, in case of reduction reaction, note that anytime you reduce an aldehyde functional group, you form a primary alcohol. Anytime you reduce a ketone, you form a secondary alcohol. Take note of that. Then the fourth reaction to look here is the reaction of carbonyls with organometallic reagents. And organometallic reagents here, we have the alkyl lithium, and then we have the Grignard reagents. These two are organometallic reagents because you see metals like magnesium bonded to an alkyl residue, or lithium bonded to an alkyl residue. So they are referred to as what? Organometallic reagents. Grignard reagents, or lithium, alkyl lithium reagents. So when they react with what? Aldehydes and ketones, they form a new carbon-to-carbon bond, and that also leads to the formation of what? Alcohol after hydration. So there are some examples here. It says give the product of the following reaction. Now, if you have this ketone here, and then you perform reduction reaction, you are going to form what? A secondary alcohol. Now, if you have a ketone here, the reaction will take place here. Now, the first one is there's a Grignard reagent here. So if this ketone reacts with what? This organometallic reagent, then what it means is that you are going to form an ether, okay? Because the alkyl chain here will join to the oxygen group here, and then you form that product. So you can try your hands on that. We also have the cyanohydrin formation, and the cyanohydrin simply means when you have the cyanide functional group bonded to the same carbon as an alcohol functional group, a hydroxyl group. So you have an OH and the cyanide group bonded to the same carbon. We refer to that one as what? A cyanohydrin. So when you have a ketone or an aldehyde, when you react with what? Sodium cyanide, definitely the sodium metal will be plus, the cyanide will be minus. So the cyanide, which is nucleophilic, will come and attack the carbonyl carbon here, and then the carbon double oxygen will break, and then you get the alkoxide ion forming, and when you hydrolyze within acid or with an acid, then you form the alcohol OH, and then the cyanide also is bonded, and that is cyanohydrin. 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 So here, this is an aldehyde. So you introduce cyanide, and then you introduce alcohol. So this is a cyanohydrin functional group. The cyano group of a cyanohydrin is readily hydrolyzed to a carboxylic acid by heating with aqueous acid or base. So after forming cyanohydrins, if you oxidize the cyanohydrin, the cyanide group, the C triple bond N, is converted to what? A carboxylic acid. Is converted to a carboxylic acid. And this is just the mechanism, which I keep on saying that at this level, you will not be told to show the mechanism of such reactions, but they are here to help you appreciate and then understand the concept behind those reactions better. Then the fifth reaction of aldehydes and ketones we want to look at is the Wittig reaction. It is the olefination of carbonyl compounds with a halide. Okay, and the halide, the common one is what we call the triphenyl phosphine halide. Okay, you have 3 phenyl groups on phosphorus with a double bond with what? C, and then 2 alkyl groups. So this one can be aldehyde or ketone. And so when you have an aldehyde or ketone reacting with a halide, what it means is that you are going to form a carbon double bond carbon, okay, and then, but then that depends on the, what do you call it, the 2 starting materials. Over here, you are forming this alkene, but then the alkene that you are forming, we are saying that, look at the C, the one with the blue background or painted blue. That is the group that is from the aldehyde or ketone, which is going to form a double bond with what? The red portion here of the halide. So you form your alkene. Then the C6H53, that's a triphenyl phosphine group here, will form a double bond with the oxygen here, which is called the triphenyl phosphine oxide as a byproduct. So Wittig reaction leads to the formation of what? Alkenes. And the type of alkene that is formed is dependent on the aldehyde or ketone as well as the halide. The halide preparation is what is being described here. So phosphorus halides are prepared by the reaction of triphenyl phosphine with an alkyl halide to produce the triphenyl phosphonium salt. And that you can then go ahead and use it in forming your final product. So these are all applications of Wittig reaction. And so when you get the slides, please do go through and then try to understand the principles behind that. Now we can also add alcohols to aldehydes and ketones. And when you add aldehydes to alcohols, or alcohols when added to aldehydes and ketones, you form what we call the hemiacetals. Okay, you form what we call the hemiacetal. But before the alcohols, water can also be used. You can hydrate an aldehyde or ketone, all right? And then you form the hydrates. And when an alcohol is used, you form the hemiacetal, and then the hemiacetal group. Please, a minute, hold on. All right. So I was talking about the ketal formations, the hemiacetal, the acetal, and then the ketal formations. And these are a summary of those ones. So we have cyclic acetals formation, which is formed when a ketone or an aldehyde is treated with an excess of 1,2-diol. So this is the diol, and then this is the aldehyde or ketone. Can you see my cursor?
Doc. Yes, Doc.
So this is your diol, and this is your aldehyde or ketone. So it forms a cyclic acetal. Okay, and usually these ones are used as what protection. For those who are doing natural product chemistry with me, we talk about when you have a carbohydrate with an aldehyde, alcohol functional group, a ketone functional group, and then you want to perform a reaction only at one point of the functional group, maybe the aldehyde, then you need to protect the other one so that they are also not what oxidized or reduced. So the acetals are stable in basic, and so they are employed as what protecting groups. As you can see in sugars, sucrose, which is a table sugar, has 2 acetal groups. Okay, has 2 acetal groups, and when you get a slice, try and be very conversant with them. Primary amines react with aldehydes and ketones to form what we call the imines, while secondary amines yield what we call the enamines. These ones, please, at this level, we will not go into the imines and then the enamines, okay? But what you need to know is that when an aldehyde reacts with an amine, it forms the imine, and when a ketone reacts, it forms what? The enamine. So note just that. And these are all examples of the imine formation and then the enamine formation. All right. So please, this is some selected reactions of aldehydes and ketones as far as this course is concerned. And so when you get a slide, please take your time and go through. Have I given some tutorial or review questions to you on this course?
No, Doc.
Okay.
No, sir.
Because it helps. It
No,
says
sir.
that with all these
No,
plenty
please.
reactions, with all these plenty reactions we are looking at, when you are learning, the question is how questions can be coined out of them. So maybe I will do well, and then before this weekend ends, start sharing some review questions so you can be guided by when you are looking at all these reactions. For organic chemistry, it's very simple, just that you have a lot of reactions to deal with. And most of the reactions, you need to remember the reagent, the condition, and then the product. So we are done with the carbonyls, aldehydes, and ketones, and we have to move to the carboxylic acids. Now we will look at the carboxylic. Yes.
Doc, my hand is up. I wanted to say that if with the tutorial questions, I wish you also ask subjectives.
All right. Let's see how it goes. I will do that. So please, like I keep on saying, let's not let the lecture time be the only time that you probably will sit down and go through. The reactions that I'm exposing you to are many, so you need to be practicing continuously Yeah, so you'll be very conversant with most of them. So I will share the slide with you as I did with the various center reps. Sunyane, Borga, St. John's, Takrade, Kaswa, and then Ho, as well as Seville also. I will share this material with your reps, and then they will give it to you, as well as the review and tutorial questions.
But please, Doc. Please, Doc. Please, Wesco is also
Yes.
here. Please. Yeah, Wesco is here.
Wesco, are you done with your
Yeah,
lecture?
yeah, yes, please. So
You are
we
supposed to
wanted to
be.
also join.
Are you,
Oh,
are you finished with your lecture?
but Doc, we normally like. Yeah,
Somebody
we
is there.
started but we
Somebody.
didn't finish. Yeah. So please try to also
So Wesco, where
share
did you
the
rate?
very well on
Where have you rate?
Doc.
Yes.
Hello, Doc.
Yes.
Wesco, we have, yeah, we were doing we were doing
Uh-huh.
the reactions. We are doing the reactions
Oh,
of aldehydes and the ketones.
okay. So there's no need
Yeah,
of
yeah,
coming here because you are doing the same thing.
yeah. We wanted to have more of the lecture.
Anyway,
Yeah, Doc.
officially,
Yeah. We wanted to have more of the lecture.
officially, I can't be giving you direct materials. If anything at all, I have been giving the lecture slides to the tutors, and I hope they have been sharing with
Yes.
you. So the
Yes,
review
please.
questions and the tutorial questions, I will
Uh-huh.
share with your tutors,
Yeah.
and they will make you get them. I
Okay.
hope that's fine. All right.
Yes, yes. That's fine. That's fine. Thank you very much. Thank you.
Welcome. Please, can you see my slide?
Yes, please.
Yeah.
Yes,
Yes.
please.
No.
Yes.
Yes. Your network is bad. Please just position yourself well and then talk. Oh no. All right. So please, before we start with the carboxylic acid, let's give ourselves some 5 minutes, 10 minutes break, please. Let's give ourselves some 5-10 minutes break. Okay. Then I will come and start the carboxylic acids. Thank you. David, please exit and join again. Your network is bad. When we come back after 10 minutes, I'll take your question. Okay.
Hello, please, what is happening?
We are on break for 10 minutes. Yeah, we are on break.
Okay, thanks, dear. Yeah, thank you. My network also, I didn't know what's happening. Thank you.
All right. I think we should continue. Are you all back?
Yeah.
Is the 10 minutes not up?
Yeah.
Yes.
Yes, Doc.
So carboxylic acids are another group of what? Functional group, organic functional group, or organic compounds with a particular functional group. So from alcohols to ethers to epoxides to aldehydes to ketones, we are introducing to another functional group, that's the carboxylic acid functional group. And these carboxylic acids are said to be organic acids. And organic acids are weak acids. They are not as strong as the mineral or the inorganic acids. They are weak acids. Now, organic acids are characterized by the presence of the carboxyl functional group. The carboxyl functional group. And this is the carboxyl functional group, COOH. So anytime you see an organic compound with this functional group, then it is not an alcohol, it is not an aldehyde, it is not an ketone, it's not a ketone, but it is what? An acid, a carboxylic acid. And these carboxylic acids are characterized by this functional group. There could be one or more of the carboxyl functional group. Now, this carboxyl functional group can have the carbonyl functional group and then the hydroxyl functional group. So the alcohol functional group, that's the hydroxyl, then the carbonyl functional group, the two together is what makes up the carboxylic functional group. Now, the general formula of carboxylic acid is R bonding COH, where R is an alkyl or area group. It can be an aromatic ring or an alkyl chain. Now, carboxylic acids are Brunstelloy acids because they are proton donors. You know, when we say an acid is any substance that produces the hydrozonium ion or the hydrogen ion in solution. And so this carboxylic acid are able to generate these H plus ions in solution. So of course that makes them what? Acid. But specifically we're saying that they are Brunstelloy acids because they are proton donors. So if you see ethanoic acid as a 2-carbon acid, in solution, you form the ethanolate ion as the conjugate base and the hydrogen ion, which is the proton or the acid proton. Where do we find some of these acids? Where we find some of these acids? All right, so sources of carboxylic acids, or some common carboxylic acids, and where they can be found. We have the formic acid or metanoic acid. That's like one carbon carboxylic acid. And formic acid or metanoic acid is found in ants. It's found in ants. This type of ants, they contain a lot of what? Formic acid or metanoic acid. Then a 2-carbon acid, called the ethanoic acid or acetic acid, is also found in vinegar. It's also found in vinegar, and that is what gives vinegar its sour taste. Ethanoic acid is what gives vinegar its sour taste. So beyond the metanoic and then the ethanoic acid, we can also have acids with 2 or more carboxyl groups, and they are called carboxylic, dicarboxylic. If there are 3, tricarboxylic, and so on and so forth. And the simplest dicarboxylic is the oxalic acid. You can see that it's made up of 2 carbons, but with 2 acid functional groups. It is like this, or if you expand it, that is oxalic acid. It is a dicarboxylic acid because it has 2 carboxyl functional groups. Mellitic acid is an example of a hexacarboxylic acid because mellitic acid has what? 1, 2, 3, 4, 5, 6 acid functional groups, one to an aromatic nucleus. So it is what? A hexacarboxylic acid. Tartaric acid is a dicarboxylic acid. It has 1 and 2 carboxylic functional group. Then you have citric acid, which is found in fruits, the citrus fruit, orange, tangerine, and the rest. They are tricarboxylic acid, meaning they contain 3 carboxylic acid functional groups. Now, how do we name carboxylic acids? IUPAC naming. How do we name carboxylic acids? You are supposed to select the longest continuous carbon chain that contains the acid functional group. Then you will consider the corresponding alkane name. So if you consider the one we are seeing on our screen here, the carbon chain starts from here, 1, 2, 3, 4, 5. It contains 5 carbons. So the corresponding alkane name, a 5-carbon alkane, is pentane. Pentane. Now to get the acid name, the word pentane, the last letter E, you omit it and you replace it with what? Oic. O-I-C. Oic. Oic. So it becomes what? Pentanoic. Then you add the word acid to it. So you have what? Pentanoic acid. So if it is a 3-carbon acid, it becomes what? Propanoic acid. 4-carbon butanoic acid. 6-carbon hexanoic acid. 7-carbon heptanoic acid. 8-carbon octanoic acid. So the longest chain containing the acid functional group, when selected, and you get to know the number of carbons in there, you consider the corresponding alkane name, omit the last letter E in the alkane name, and then replace it with what? Oic. O-I-C. Then you add the word acid, and that gives you the IUPAC name. Now, aside this, if there are 2 of the carboxylic acid functional groups,
Then the longest chain should contain both. And then you number the chain so that you know the position of the two acid functional group. It could be 1,6, it could be 1,5, it could be 1,4, depending on the numbering of the acid groups. And the acid functional group is always at the terminal, like the aldehyde. So you start numbering from one end and then you end at the other end. If you have a 5-carbon acid with 2 acid functional groups, and the acid functional groups are on position 1 and 5, then you number it 1 and 5, and it becomes what? 1,5-pentane dioic. Dioic means 2 of the acid functional group. So it becomes 1,5-pentane dioic acid, or 1,4-butane dioic acid, and so on and so forth. Now, after selecting your longest chain containing the acid functional group, any other group that does not form part of the chain is considered a substituent group. And from our previous knowledge, we know that when the substituent groups are different, we have organic and the inorganic. You name the inorganic first before the organic. And when you have multiples of the inorganic, you arrange them in alphabetical order. And when you have multiples of the organic, you do same, arrange them in what? Alphabetical order. So the examples you can see on the screen, this is pentanoic acid. And because the longest chain, the numbering always starts from the acid, and the acid takes the position 1, like the aldehyde, we normally don't bring the position of the acid to say 1-pentanoic acid, or you can say pentan 1-oic acid. No. We all know that the acid functional group, because it's at the terminal end, it will always assume position 1. So if you take this one, the acid functional group is this. The longest chain is 1, 2, 3, 4, 5. Also what? Pentanoic acid. But then because of the substituent group here, you have to number. So you have 1, 2. So the substituent chloro is on the second carbon. So we have what? 2-chloropentanoic acid. Over here, the longest chain is 1, 2, 3, 4. So that will be butanoic acid. 1, 2, 3, 4. Butanoic acid. So if you select the 4, then you have a methyl group as a substituent. Then you number the chain. 1, 2, 3, 4. So the methyl group is on the position 3. So that becomes 3-methyl butanoic acid. So apart from the IUPAC name, these are some common names of some carboxylic acids we need to know. Formic acid is a 1-carbon acid. Acetic acid is a 2-carbon. Propionic acid. These are all common names. Butyric acid, valeric acid, caproic acid. These are all common names. So in as much as we have learned how to name acid by the IUPAC system, it is also important to be conversant with some of these common names. Now let's look at the structure and properties of carboxylic acids. The structure and properties. So this is the acid general formula. And the distinctive feature of carboxylic acid is the carboxylic acid group. And that can undergo what we call mesomeric effects, where the lone pair of one of the electrons on the OH can form a double bond here, and then the carbon double bond oxygen will break here, and this one can form back the double bond, and this one will break and form the OH. So this resonance structures is what we call mesomeric effects. Mesomeric effects. We say carboxylic acids are weak acids because they are organic acids, and all organic acids are weak acids. And so we want to look at the acidity of carboxylic acids, and an acid strength when you want to compare maybe two or more acids. So if an acid dissociates in water, you form the carboxylate ion and then the hydrozonium ion. And then the carboxylate ion is able to stabilize itself by resonance, making the acid strong. So there is a constant called the dissociation constant. And here, if you are talking about dissociation of an acid, then the constant becomes what? The acid dissociation constant. And the constant, that's the dissociation constant, is equal to the product of the concentration of the two products. That's the carboxylate ion here, the concentration of this carboxylate ion, the concentration of what? This hydrozonium ion, a product of the two, divided by the concentration of the acid and that of water. Okay, but then water concentration is taken as what? Units. That's 1. So you have to move that one to the K, and then you then will define the constant as what? The Ka. And Ka is acid dissociation constant. K is what? Dissociation constant. Ka is what? Acid dissociation constant. So the Ka is equal to the dissociation constant times the concentration of water, which is considered as what? Unit 1. And that one is equal to the concentration of the product ions, that's the hydrozonium and then the carboxylate ion, all divided by the concentration of what? The acid. And that gives you what? The Ka. Now, if you know the Ka, then you can find what we call the pKa. And the pKa is what? Negative log base 10 of the Ka. So if you know the value of Ka, just with your calculator, you punch negative log base 10 of the value of Ka, and that gives you what? The pKa. And the value of pKa tells us about the strength of the acid. The value of the pKa tells us about the strength of the acid. And that the lower the pKa, the stronger the acid. The lower the pKa, the stronger the acid. So when you are given a group of acids with their pKa, as you can see here, formic acid 3.77, acetic acid 4.76, propionic acid 4.88, and the rest, you could see that the formic acid's pKa is smaller than the acetic acid. So formic acid is stronger in terms of acid strength than acetic acid. That's what it means. And later we'll see why the formic acid is a stronger acid than what? Acetic acid. Now, there are some factors that affect the strength of an acid. There are some factors that affect the strength of an acid. And these are the factors we want to look at briefly. Now we have what we call electron withdrawing groups, and then electron releasing or electron donating groups. We have what we call electron withdrawing groups, and then we have what we call electron releasing groups. Please, these two groups of what? Atoms or group of atoms were made known to us when we're doing the the introduction to organic chemistry. But then I think I will touch briefly on some of them here. But before then, any group that is an electron withdrawing group that is found on a carboxylic acid makes the acid more stronger. It strengthens the acid and weakens the bases. And then the electron releasing or the electron donating group, they perform the opposite. When they are found on any carboxylic acid, they turn out to weaken the acid. They make the acid very weak. But then they rather strengthen the bases. So what we need to know is to be able to identify when we see an electron withdrawing group and when we see an electron donating group. And that the electron withdrawing groups, they make an acid stronger. So the more you see some of them, then that should tell you the strength of the acid. And then when you see the electron releasing groups or donating groups, they make acids weaker. When you see them in an acid, then that should tell you their impact or effect on the strength of an acid. So if you take acetic acid, a 2-carbon acid, okay, the pKa is 4.76. It means it's a strong acid. Then look at the acetic acid here, or the ethanoic acid, the 2-carbon acid. You see, apart from the acid functional group, the next carbon, which has 3 hydrogens, in the second one of the hydrogens has been replaced with chlorine. In this third one, 2 of the hydrogens have been replaced with 2 chlorines. Then in the third one here, all the 3 hydrogens here have been replaced with chlorine. And the interesting observation here is that the more chlorine atoms are being added, the lower the pKa value. The more chlorine atoms being added or being substituted on that acid, the lower the corresponding pKa. And I've indicated that the smaller the pKa, the stronger the acid. What it means is that a pKa value of 0.65 is stronger, it's an acid which is stronger than 1.29. And 1.29 is also an acid which is stronger than 2.86. And 2.86 is an acid which is stronger than 4.76. The question is, why is it so? It is so because the chlorine that is being substituted on the acid by removal of hydrogen is an electron withdrawing group. Chlorine, like the other halogens, bromine, fluorine, iodine, they are all electron withdrawing groups. And so when they are found in an acid, they make the acid stronger. How do they do that? Now, the acid is an acid because of its ionization in solution. So the ability of the oxygen-hydrogen bond to break, to release H+ ion, that makes the compound acid. Now, for the chlorine atoms, you realize that instead of they donating electrons to stabilize the oxygen-hydrogen bond so that the hydrogen will not be ionized, and for that matter, the acid to be weak, they rather are drawing electrons. They are rather drawing electrons to themselves. That's why we say they are electron withdrawing group. Drawing electrons to themselves makes the oxygen-hydrogen bond even more weaker and weaker. And that means that the hydrogen is easily ionized or released in solution. And that makes it a stronger acid. Of course, the more H+ ions you're able to release, the stronger the acid. But then you see, here we had 1 chlorine, here we have 2, here we have 3. So the combined strength of 2 chlorines during the electron withdrawing is going to be more felt than 1 chlorine. And for that matter, the combined strength of 3 chlorine atoms withdrawing electrons will be much, much felt than 2 chlorine atoms. So the more the number of electron withdrawing groups, the stronger it favors the acid strength. And that is what you can see here. So in the other sense here, you could see that the 2-carbon acid, the hydrogen, one of them is replaced with a methyl group. and then the chain becomes 3 carbons. Then 2 hydrogens have been replaced with 2 methyl groups. Then all the hydrogens have been replaced with what? 3 methyl groups. Now, a methyl group, like all other alkyl groups, they are not electron withdrawing groups. They are electron donating groups. So what it means is that the more alkyl group you bring, the more methyl chains you are introducing, then you are making the acid what? Weaker and weaker, because these alkyl groups or these methyl groups donate electrons to go and stabilize the oxygen hydrogen bond there, therefore not making it what? Easily ionizable. And that will affect the acid strength and it becomes weak. So at this point, if you are giving 2 or more acid to tell or to arrange which one will be more acidic, then if there are some substitution on the acid, you should be looking at what groups they are. Are they electron withdrawing groups? If they are, then they will increase the acid strength and make the acid stronger. If they are electron donating groups like the methyl or alkyl groups, then they will weaken the acid strength and make the acid weaker. So that is the type of group, whether it is electron donating or electron withdrawing. Again, proximity also comes in. If you have, let's say, 2 acids in which one of the chlorines is just on the 2nd carbon from the acid functional group, and then there's another acid in which the chlorine is far away, maybe on carbon 4 or carbon 5, then proximity, the one that the chlorine is closer to the acid functional group, its electron withdrawing effect will be much felt more, and that will make it more acidic than the one in which the chlorine atom is bonded to a carbon which is farther away from the acid functional group. Any question? If not, we will look at the physical properties of carboxylic acids.
Please, Doc, go over the last one again.
Is that a question? Is that a question? So if you say I should go over again, then please go and pick the recorded video, okay, and watch again. But in simple terms, at this stage, what I will want you to do is your ability to identify electron withdrawing group and the electron donating group, okay? I've given you some examples. All the halogens are electron withdrawing groups. The amino functional group, NH2, is an electron withdrawing group. The OH, the alcohol hydroxyl group, is also what? Electron withdrawing group. All these groups, when they are found on a carboxylic acid, they make the acid stronger because they are withdrawing electrons. They are making the oxygen hydrogen bond weaker so that the H+ ion can be released in solution more and faster, making the acid what? Stronger. But if the group that is on the acid is like a CH3, a methyl group, or an alkyl group, or it's like a nitro group, NO2, or it's a cyano group, CN. Okay, these groups are electron donating groups. So they rather make the acid weak. So your ability to identify what type of group it is, you can tell whether to make an acid strong or weak. And then comparatively, you can tell. But then I also said that if you are giving 2 acids, one of them is, let's say, 2-chloroethanoic acid. 2-chloroethanoic acid, the chlorine is on the 2nd carbon here. Okay, proximity. The chlorine is on the 2nd carbon, 2-chloroethanoic acid. Now, if I give you 4-chloropentanoic acid, 4-chloropentanoic acid, over there, there's also chlorine, but then that chlorine is bonded to the 4th carbon. So if I ask you 2-chloroethanoic acid and then 4-chlorobutanoic pentanoic acid, which one is going to be a stronger acid, then here you know that the 2 acids all have chlorine attached. So ideally, you would have wished that they have the same strength, but no. The 2-chloroethanoic acid, the chlorine is closer to the acid functional group, proximity, than the 4-chloropentanoic acid, where the chlorine is far away from the acid functional group. So the one that is closer, its effect, its electron withdrawing effect, will be felt much stronger than the one that the chlorine is far away. And so the one that the chlorine is closer, it will cause the easy ionization of the H+ ion in solution because of the effects that it will give to the acid functional group. So that one will be a stronger acid than the 4-chloropentanoic acid, in which, though the chlorine is doing electron withdrawing effect, it is far away from the acid, and so it will not be felt much. All right, so now let's look at some physical properties of carboxylic acids. And like we saw in the hydrocarbons, alkanes, alkenes, alkynes, you see, anytime you increasing the number of carbon atoms in a particular functional group, there is a corresponding increase in the boiling point. So here too, the same thing. For carboxylic acid, look at formic acid, a 1-carbon acid, and then acetic acid, a 2-carbon acid. The 2-carbon acid will have a higher boiling point than what? The 1-carbon acid. Propanoic acid has 3 carbons. It will have a higher boiling point than what? Ethanoic acid or acetic acid. So the more carbon the acid is having, the higher its boiling and melting point. Okay. But remember that in the hydrocarbons, we said that if you are increasing the carbon chain and then you start introducing branching has effect on the boiling point and melting point.
That's right.
What does it do? Branching decreases boiling point, but it increases what? Melting point. So if you have 2 carboxylic acids with the same number of carbon, but then one of the acid, the carbon chain is straight, and one of the acid, the carbon chain is branched. Okay. Then in terms of boiling point, the straight chain carboxylic acid will have a higher boiling point than the branch. But when you're talking about melting point, the branched carboxylic acid will have a higher melting point than the straight chain carboxylic acid. So just go and revise our previous knowledge. Then in terms of solubility, the lower members are completely soluble in water. You are getting some you are getting some feedback. Is there a question? If there's a question, you can ask so that I continue. I don't want the feedback. All right. So for solubility in water, definitely carboxylic acids, most of them are going to be soluble in water, but then their solubility will vary from one to the other. Why are carboxylic acids soluble in water is because carboxylic acids are polar. Okay, they are polar. And so you expect them to be soluble in what? A polar solvent like water. But we are saying that the lower members, those with fewer carbons, they are readily soluble in water. Okay. And if you look at formic acid, acetic acid, their solubility is what? Infinite. Okay. Everything. But when we start increasing the carbon chain, then the solubility starts decreasing. Okay. When we start increasing the carbon chain, then the solubility starts decreasing. So that is on the solubility of carboxylic acid. Now, how do we prepare carboxylic acids? Synthesis of carboxylic acids. Synthesis of carboxylic acids. So for the synthesis of carboxylic acids, some of them are not new to us because we had looked at some reactions of alcohols, and that when you oxidize an alcohol and it is a strong oxidizing reagent that you are using, you form a carboxylic acid, especially if you are using a primary alcohol. When you oxidize it, you get an aldehyde. The aldehyde gets further oxidized towards a carboxylic acid. Okay, so let's look at some known methods. So this one is a primary alcohol, and the hydroxyl group is bonded to this sp3 hybridized carbon, and the two hydrogens on that carbon are said to be what? Alpha hydrogens. Okay, they are said to be what? Alpha hydrogens, and these alpha hydrogens are oxidizable. They are oxidizable. They can easily be oxidized. So we all know potassium permanganate is an oxidizing reagent. You subject it to what? Heat, and then it will form this aldehyde product. But then the aldehyde also gets further oxidized to what? Carboxylic acid. So the initial color of the permanganate ion, that's the purple color, after the alcohol is being oxidized to an acid, you form the manganese 2 oxide, which is precipitate, which is what? Brownish. And that will tell you that a carboxylic acid has been formed. So all that we are saying is that primary alcohols are oxidized to what? Aldehydes, and these aldehydes are further oxidized to what? Carboxylic acid. So if we give you a primary alcohol and then a strong oxidizing reagent like KMNO4, then the final product we expect you to write is not the aldehyde product, but we want the acid product. We want the acid product. If you start with a 2-carbon alcohol, you form a 2-carbon acid. If you start with a 3-carbon alcohol, you form a 3-carbon acid. So that is that on oxidation. It is not only KMNO4, you can also use potassium dichromate, K2Cl2O7. It's also a strong oxidizing reagent. Now it has this orange color, that is the oxidizing reagent. So when you oxidize a primary alcohol, you form the aldehyde, but then the aldehyde gets oxidized further to the acid. With the formation of the acid, the chromic or the chromate is ionized, okay, to the Cr3 plus, and that is greenish in color. So when you see a greenish coloration after the addition of this orange reagent, then that should tell you that an acid has been formed. So either use the KMNO4 or the potassium dichromate. In both cases, you are oxidizing the primary alcohol to a carboxylic acid. Then oxidation of side chains. And this reaction is also known new to us from our previous knowledge in the introduction to organic chemistry when we were dealing with the aromatics. Okay, we said when you have an alkyl group bonded to an aromatics, and this alkyl group, it can be 1 carbon, 2 carbon, 3 carbon side chain, or even 5 carbon side chain. When you oxidize this side chain with KMNO4 and then heat, you form benzoic acid. Always, you form benzoic acid. So anytime you have a side chain to an aromatic nucleus, oxidation of that side chain leads to the formation of what? A benzoic acid, which is an aromatic acid. Then the third one is the carbonation of greener reagent. Now, this carbonation reaction is always like extension of 1 more carbon. So if you are starting with a greener reagent of 2 carbons, you end up forming an acid with what? 3 carbons. So the carboxylation reaction requires a carbon dioxide in ether reacting with greener reagent or lithium, any organometallic reagent. And that will give you the carboxylate ion. Now, when you have the carboxylate ion and then you hydrolyze it in acid, then that leads to the formation of what? The carboxylic acid. What is important to note here is that the carboxylation had added extra carbon to the alkyl chain. So if your alkyl chain is 7 carbon, by the time you are done with the carboxylation and hydrolyze, you form an 8 carbon what? Acid. You form an 8 carbon acid. Then formation of nitriles followed by hydrolysis. Now nitriles are from cyanide, okay? So when you have an alkyl halide as your starting material, this is your alkyl halide. So the halogen here, the chlorine here, is going to be replaced with what? A cyanide group. And the cyanide group is what? C triple bond N. And the cyanide group can be obtained from potassium cyanide or sodium cyanide. Okay, we also have hydrogen cyanide. And this cyanide group, that's a CN, replaces the halogen. Of course, that one is nucleophilic, so it will attack this carbon because the chlorine or the halogen will polarize that bond, and then that will be partially negative, and then the carbon here will be partially positive. So the cyanide ion, which is nucleophilic, will attack it, and then that will give you this. Now the R here, bonding CH2, is now joined to what? C triple bond end. Okay, and this is the nitrile. This is what we call nitrile. Okay, the nitrile formation. And after forming the nitrile, you can do what we call acid hydrolysis. Okay, acid hydrolysis, you are adding water in acid and you heat. So when you do acid hydrolysis of any nitrile, you form what? Carboxylic acid. You form carboxylic acid. Again, let me be quick to say here that pay attention to the reaction conditions, because in most cases, when you are giving an alkyl halide, sodium cyanide or potassium cyanide in DMSO, and you are asked of the product, you form a nitrile. Now, anytime you have a nitrile as your starting material and you perform acid hydrolysis, you should know that you are going to form what? A carboxylic acid. The same way you should know the product. If I give you the starting material and then the product, the reagents that did the conversion, you should also be able to what? Provide them in an exams. So here I keep on advising that yes, the reactions are a lot, but the more you practice, the more used you become with them, and then you wouldn't struggle when it is exams. Then hydrolysis of nitriles. Yes. Yes, please, I'm listening. Hello. All right, so this is another example of the hydrolysis. Okay, so this is an alkyl halide. That is an alkyl halide. So when you react it to what? Sodium can. Yes. Yes, I'm listening. So when you react to the sodium cyanide, the cyanide please, whoever is on the floor, I'm waiting for you to finish before I continue. If you have any questions. Your network is not helping. So please, if you can link up later with your question, or you can type it in the chat box. I'll respond to it. So anytime you have an alkyl halide, you react it with what? Cyanide. And as I said, it can be potassium cyanide, sodium cyanide, and then you form the nitra. The nitra is when you have an alkyl group bonded to what? C triple bond N. Then acid hydrolysis, and you heat. Then that will change the C triple bond N to what? The acid functional group. So these are all the methods. Some of the methods we really did not touch on. Remember when we were dealing with the introduction to organic chemistry, when we got to the reactions of alkenes, we said alkenes can undergo exhaustive oxidation, where you break the double bond and you form an acid. The same thing when we got to alkynes, we said alkynes, the triple bond, you can cleave it, and that when you cleave it is a strong acid, so oxidizing reagent like CHE204, you form an acid. So all the methods of preparing carboxylic acid, as you can see here, being summarized. Now we are going to look at the chemical properties of carboxylic acids. And when I say chemical properties, how carboxylic acids react. Now, the first one is esterification reaction. Esterification reaction. Carboxylic acids can react with alcohols to form esters. Okay. Carboxylic acids can react with what? Alcohols to form what? Esters. And then the ester is formed with water as a byproduct. Now, this reaction is a reversible reaction. What it means is that when you are forming the esters, the ester also gets hydrolyzed with the water byproduct to form back your acid and then the alcohol. So it means the yield is not that high because it's a reversible reaction. Okay. But then later, when we are dealing with the carboxylic acid derivatives, we'll take esters as a topic and then look at how esterification reaction is done in detail, and then how we can maximize the ester formation from carboxylic acid without having a low yield. Then the carboxylic acid, we all know, when you oxidize a primary alcohol, you get carboxylic acid. So when you also reduce a carboxylic acid, you form an alcohol. So reduction of carboxylic acids also leads to the formation of what? Alcohols. Then again, we know when you do acid hydrolysis of nitrites, you form carboxylic acid. So when you also reduce carboxylic acid, you form the nitrites. Then the same carboxylic acid can react with what? Acid chloride. Sorry, they can react with what? Thionyl chloride. That is SOCl2 or PCl3 or PCl5 to form acid chlorides. Please here, I'm just giving you a general picture and a summary because we are going to pick all these acid derivatives and deal with them in detail. And that is where maybe I'll throw more light on it. Again, we know aldehydes are oxidized to acid. So if you want to reduce a carboxylic acid to an aldehyde, then you need a reducing reagent. Just that, you need a mild reducing reagent. You don't have to use a stronger one like lithium aluminum hydride. You can use a milder one like sodium borohydride. Because if you are not careful and you use a strong reducing reagent, the aldehyde will also be further reduced to what? A primary alcohol. Then the carboxylic acids can react with what? Ammonia, primary and secondary amines to form what we call amides. When it reacts with ammonia, you get a primary amide where the nitrogen is having two hydrogens. When it reacts with what? Primary amine, you form the when it reacts with secondary amine, primary amine, you form the secondary amide. And when it reacts with what? Secondary amine, you form the tertiary amide. The classification of amide will also be looked at in due course. Then carboxylic acids, per their name, they can react with a base. Let's say sodium hydroxide to form the salt form of what? The salt. Okay, so you form sodium salt of what? Carboxylic acid. Okay. So these are a summary of all the reactions that acids undergo. And most of these reactions lead to the formation of what? Acid derivatives. They lead to the formation of what? Acid derivatives. So I talk about esterification. I said it's a reversible reaction. You form the ester with water. Now this water can hydrolyze the ester and break it back to form the carboxylic acid and alcohol. So usually the ester formation is of a low yield. But if you want to get a high yield, then first of all, you can convert your acid to what? Acid chloride by reacting this one with tannal chloride. And then before you bring in the alcohol, and then this time around, you are forming the esters with what? ACl. And ACl cannot hydrolyze an ester. So you form a higher yield of your product. And that is what you can see here. So reaction of carboxylic acid with tannal chloride. We say this is a neat reaction. It's a neat reaction because when you form your acid chloride here, which is your main product, the two other byproducts, the SO2 and then the ACl, they are gases. So once you are forming these products, the gases can be made to escape, leaving behind the acid chloride product. So after the formation of this product, you don't worry yourself to do even any workout because your product will just be only the acid chloride forming. But if you don't use the tannal chloride, then you go and use PCl3, PCl5, you also will form the same product. But then the PCl3 and PCl5 gives you some byproducts which will require some hard work. You have to do some workout by cleaning those side products before you can get your pure acid chloride. And in so doing, you end up losing some of your acid chloride products, and that can affect the final yield. So again, carboxylic acid can be used to prepare acid anhydride. What you do is that you can convert one of the acid to an acid chloride and then convert the other one to what? The sodium salts. And then the two of them, when they react, you form your acid anhydride. You form your acid anhydride. And that is a very good method for preparing anhydrides. Then I've also talked about the amides. I said when ammonia reacts with an acid, you form the primary amide. When a primary amine reacts, you form a secondary amide. When a secondary amine reacts, you form what? A tertiary amide. When we pick the amides, we'll look at the classification of the primary, secondary, and tertiary again. But amide formation is one of the reactions of what? Carboxylic acids. Then we talk about the neutralization reaction of carboxylic acid. Because they are acids, they can react with a base. And when they react with a base, they form salt and water. So the salt is the sodium salt of the carboxylate ion, and then water as a byproduct. So this is just a simple acid-base reaction. One is an acid, one is a base. So you form what? Salt and water. But this sodium acetate carboxylate salt is used as a preservative and a flavor enhancer in most food, canned foods, and then food products. Then in the reduction reactions, we said that primary alcohols are oxidized to carboxylic acid. So you can also reduce the carboxylic acid to primary alcohols using a strong reducing agent like what? Lithium aluminium hydride. It is a very strong reducing agent. So when you add it to a carboxylic acid, it will reduce it to what? A primary alcohol. A primary alcohol. But then, if you don't want to reduce the acid to a primary alcohol, but you want to leave it in an aldehyde product, then please, you need to use what? A mild reducing reagent. Okay? A mild reducing reagent, not a stronger one. Because for a stronger reducing reagent like lithium, aluminum hydride, it will reduce the acid straight to the primary alcohol. But if you want to reduce it to an aldehyde, then you use a mild reducing reagent. An example is lithium aluminum tritetbutoxyhydride. Okay, the name is very long, but then it is a mild reducing reagent. Lithium aluminum tritetbutoxyhydride. This can be used, and then that will reduce your acid or your acid chloride or any acid derivative into an aldehyde. This last reaction normally is not encouraged even for us to introduce it because it's very toxic and explosive. That is isomethane formation. And so this one, you can just ignore this one. So these are the reactions of what? Carboxylic acid. And that ends the first part of the carboxylic acid. Please, do we continue with the second part of the carboxylic acid, or we do that next week? Because we are left with the acid derivatives and the amines, which basically is meant for next week. But if you so want us to continue, because I think I had wanted us to close at 5.
Hello, sir.
So we can still continue. Yes.
Sir, please, I think we can continue next because because of bad network, we couldn't complete our physics class. We are supposed to start from this evening. So maybe if we can pause here and go and rest for a while.
Okay, so
Thank
some
you.
of you will be having some makeup lectures.
Yes, because of bad network. We are starting at 7.
All right. So I think, yes.
Please, next week is the last week for the lecture, so I don't know if we can finish with this.
Well, if you are not able to finish, you can read the rest. I'll give you the materials out and you read yourself, okay? But then on my part, I will do well to finish maybe the first part. I'll use 1 hour to finish with the acid derivatives. Then I'll move to the amines, and we should be able to finish. Okay, we should be able to finish.
Okay, thank you, Doc.
But then I will share the slides with you, and please read ahead so that when we meet next week, we don't spend much time, and then we will be cool to go. So we will end here, and then next week I will take the derivatives of acid briefly, and then we jump into the amines. Thank you for coming.
Thank you, Doug.
Thank you very much, Doc.
Thanks for your time.
Bashiru mi Yusuf shaking them song my baba.
This guy, Adams.